All right, everyone. Good morning. Let's go ahead and get this session started. So to begin with, we will have Eva Silverstein talking to us about time-like space-time boundaries, holography, and phenomenology.
Well, thank you very much. And first, I want to say congratulations to Katie and everyone here for the new center. It's an amazing thing. I've enjoyed the conference um, very much so far, and congratulations on all of it. So we all miss Steve Weinberg. I'll get in a moment to my wonderful experience with him. But first, I wanted to make sort of an independent measurement of his importance. So I managed to do that on the internet, which, as you can see, shows that people search also for Isaac Newton when it comes to Steve Weinberg. If you search for various people in this room, you'll find other people in this room, but rarely, if ever, will you find Isaac Newton among the output of such a search. It's an interesting group here, but anyway, let's keep going. So much has been said about Steve's contributions, which are so important that we all know them very well, so they need not be repeated. My own interaction with him started mainly after the discovery of the cosmological constant, and many of us grappling with that. So there was a conference in Cambridge called, rather optimistically, Expectations of a Final Theory, that Steve started us off on with a wonderful piece kind of updating his views on that problem and how the interpretation as a selection effect might work in the context that we were developing of the string landscape. So, this range, his dynamic range from developing the correct model of particle physics to thinking very logically and systematically about every topic, including the cosmological constant, was, of course, a rare and beautiful thing. Although it was a little weird to have my first sort of deep encounters with Steve be not, particle physics details, but the multiverse. Still, it was a great interaction. So, as has been said, one of his many strengths was being systematic about things, and that was his main style. And I'd like to think that the topic I've chosen for today is in that spirit. So we're going to look at gravity, space-time, but be more systematic than we have before about its topology. And you might think this is an old subject, and it is, but the business I'm going to explain about including time-like boundaries in the universe is a really underdeveloped thing, and it's very beneficial for understanding formal topics like the holographic duality, while also stimulating a new phenomenological analysis of signatures. So I'm going to try to summarize that for you today. So here are my wonderful collaborators on these investigations. And let me just get started. Okay, so we all know GR. It's one of the pillars of this center. The thing, as I say, I'm going to focus on here is the prospect of time-like boundaries in GR more generally than has been studied before, where theorists have often focused on that, at least formal theorists, in a kind of extreme case of anti-de Sitter space with an asymptotic time-like boundary. In fact, time-like boundaries are available much more generally than that. They need not be asymptotic. They can be finite and time-like. The first order of business is to derive a good variational principle for that, and that's a well-known thing. The Gibbons-Hawking-York term in the action supplements the bulk action. And the particular coefficient here depends on exactly what boundary condition you choose for the time-like boundary. And I want to stress, we'll get to some sort of fancy motivations for this and fancy results we get from it. But one motivation is, again, being systematic and thinking about the generic case. So time-like boundaries, if they make sense, are the generic case, and we should not, for example, with the positive cosmological constant, we should not assume we're dealing with global de Sitter. We should consider instead all the possible topologies that are available given our cosmological constant. Okay, so there are some subtleties with this. It's not just a matter of a good variational principle, it's also a matter of a well-defined solution to what's called the initial boundary value problem, which is what it sounds like. You need to have unique evolution from boundary data that you specify inside the patch that you keep. So you have some boundary that's excising what could have been more of the space-time. And so you need a good initial value problem that respects the boundary conditions. So this doesn't always work, but there's wide classes of boundary conditions for which it does. And there's been a good deal of study of this. I say it's underrepresented, and I think that's true, but there are pioneers of this subject, both in the physics and mathematics communities that I've listed a bunch here. And there's a particular mathematician, Michael Anderson, that has pioneered probably the most systematic study of this. And those of us into this area have been enjoying various meetings on the subject to really grapple with what the status is. So here's the kind of issue you get into. You want both existence and uniqueness of solutions consistent with the boundary conditions. So that can fail. So one way it can fail is familiar. So if you think about the constraints of general relativity in the usual way, where you evolve from some initial data, well, you can't have an arbitrary choice of initial data. You have to solve the constraints. And there are sort of radial versions of the constraints if you want to specify boundary data and evolve radially, or spatially, let me call it. There's something similar. So there are equations that we sometimes call radial constraints. There's some official name for these, but they have a similar form, and you can easily see that if you choose arbitrary initial or radial data, arbitrary initial conditions on this radial boundary, then you can't always find solutions, but there are plenty of situations where you can. The other main issue is what's called geometric uniqueness. So if you have a boundary, which means, again, you've in some sense excised what could have been part of the space-time, you can have the following phenomenon. So at the boundary, you're, say, freezing. Let's consider, I should have said, the most naive case of a Dirichlet condition where you're fixing the intrinsic geometry of the boundary. Because you're fixing that, the gauge transformations that you normally have in the bulk of space become global. So if you had some mode that would be meaningless outside the patch in this picture, sometimes it can happen that it effectively propagates to the boundary and becomes physical and leads to a non-uniqueness of the evolution, having specified the initial data just inside the region. So that's an issue when it comes up. It happens if you have strictly a flat boundary and in Minkowski space. But there are many situations, including just having a spherical boundary times time, which I'm calling a cylinder here, where that is evaded. Sometimes people argue that if you go to arbitrarily short scales, it reverts to the flat case where there is this issue, but that order of limits is really not justified. In fact, in this situation, a boundary is a short scale feature, so it's UV sensitive, and we have no business taking, say, the angular momenta or the momenta arbitrarily high in energy here. So, in fact, there's an important work by these authors that shows how having a spherical boundary evades the known problem with the flat corner, it's called. Okay, so there's some, important consistency conditions. They can be satisfied even for Dirichlet boundaries. And there are other choices of boundary conditions that are quite interesting as well. Okay, so what does this have to do with physics, aside from genericity? So here's a cartoon of some aspects of cosmology. We know that the positive cosmological constant leads us to a cosmic horizon with important properties. First and foremost, it gives a theory of the origin of structure, thanks to several of the people in this room. And that matches observations beautifully, and we're trying to make the most of that in early universe cosmology. Formally, the horizon also, there are arguments going back to the 1970s that it's associated with a ginormous count of states, much like you might be aware for black holes. And it's been a question what the meaning of this is, and that's one of the things I'm going to try to lay out for you today. So how do time-like boundaries affect this? Well, with the motivation of genericity and also what I aim to tell you about regarding formal quantum gravity and the question of this entropy, it's interesting to ask phenomenologically on this side of the board, what do we know about that in our real universe? And of course, there's some bounds that we can immediately identify just from our existing data, but it's entirely possible that some small boundary exists even in our patch of the universe that we see, if it's small enough and at low enough density. So this is the phenomenological side of what I want to explain to you is a program to actually nail down what the strongest constraints are that we can put on this, which means there's also the logical possibility of some discovery potential here. So I'll start with that so as not to lose everybody in the more sort of fancy holography stuff. But both of these effects of time-like boundaries are, to me, quite interesting. So let me start with observations. What could we do to nail down the strongest constraints and potentially discover such things? First, let me explain why it doesn't overlap with what's been done before. So here's a picture of de Sitter space. It's a Penrose diagram. You could imagine putting a constant size sphere at all times in an observer patch, this red line that I've placed here. And the region that this excises includes the pole of de Sitter space. So this could be a time-like observer trajectory in the usual picture of global de Sitter. And we've put a small sphere around that and excised it. Now, it's behaving in that way that it's kind of surrounding a time-like trajectory as if it's a massive particle. However, it by itself does not warp the space-time the way that a massive particle would. So it's a distinct thing. It's not a ordinary stress energy source. And that's sort of clear from the start, but I just want to disambiguate them for this phenomenological approach. Okay, so that when you start thinking about this, there are many cases. As usual, we could be left with some small density of these in our patch. They could have affected inflationary perturbations somewhat outside of that. And with a bunch of people, including our new faculty member, Oliver Philcox, we've been starting to play with what the effects would be. So here's what it would do within our observable patch to the CMB, and it's a simple geometric point. You can think of this sort of like you might think of lensing. Light can come to us in two ways, directly and having bounced off the boundary. If you look at what happens to the last scattering surface, which normally in this picture would just be a sphere, depicted here as a circle, the boundary is in the way, so we can't see the stuff back here. And if you think about the way that the light can graze the boundary, bounce off the boundary, and reach the observer, the last scattering surface geometry instead deforms to this thing that's drawn in blue here. And so this very short scale piece of the usual last scattering surface is compressed into a region that has shorter scale modes. So if you look at a Gaussian random field without the boundary and one with, in this quite exaggerated picture, you can see the feature here. So there's going to be some proper way to optimally test this that we aim to pursue, but this is the kind of effect that we could get. In inflationary fluctuations, we simply redo the calculation starting with the Gaussian perturbations in the slightly less symmetric case where we have such a boundary. You can play with image charge methods to supplement the usual Green's function with contributions that inject some anisotropy that then can be also tested in the data. One interesting thing that people have looked at, and this goes back to some of the pioneers of the subject, Meroff and company, is certain kinds of instabilities that can occur. Now, one thing they found is that in Minkowski space, a Dirichlet boundary can have linear instabilities. However, when you place that in this de Sitter context, you find that those instabilities tamp down. So the mode solutions of some growing mode become instead the ones of the usual de Sitter mode solutions for inflation, which reach some maximum and stop expanding, stop going unstable. So it's kind of like there could be a stronger effect, but it's a bit it's a bit tamped down by de Sitter. This is kind of familiar from the proof of the stability of Kerr's black holes, which was done first in de Sitter for similar reasons. So anyway, this is just the beginning of an investigation, and it seems clear there is a lot of room to derive the proper constraints on this kind of defect in the real universe. So let me move now to the more formal side of things. Since Juan talked about tabletop experiments, I guess this is the first formal talk. Sorry, that was meant to be a joke. So GR gives us all this wonderful dynamics, including, of course, horizons, black hole horizons, cosmic horizons. And just going back into history, there were pioneering calculations in the 1970s giving an indication that there's a thermodynamics associated with it, and this has been refined over the years with a great interest in getting a statistical interpretation of those calculations. So just let me flash this thing, which I think people are aware of. If you look for black holes, at the dynamics of them, they behave very much like a thermodynamic system with the various laws of thermodynamics, and the horizon area and Planck units giving you a notion of entropy. So it suggested that indeed there should be a statistical count of these states, and that happened in string theory, which led in part to the ADS-CFT correspondence, in which it is made very, very precise. Now, in the 70s, people also, Gibbons and Hawking in particular, argued that there's also an entropy associated with the cosmic horizon. So one formal way of saying that is they looked at a path integral calculation of what should be interpreted, they say, as a partition function, whose saddle takes the usual thermodynamic form. In global de Sitter, the energy is zero. We'll come back to what we get instead with time-like boundaries where the energy is meaningful. And they could sort of easily thereby read off the entropy from their calculation. This is, again, given by the area over 4 times the Newton constant. And the suggestion of that, much like for black holes, is that a finite set of states should capture the observer patch, which is defined by that horizon or vice versa. People lately have been computing corrections to this, and that's an interesting endeavor in order to test various proposals for de Sitter quantum gravity. So it's a very live subject. So what do we really mean by this thermodynamics? It's not immediately obvious. As you know, the Einstein equations morph geometry into stress energy. It's not the naive right-hand side of these equations that counts as the energy in these thermodynamic formulas. So let me talk particularly about energy in the context of the positive cosmological constant. Okay, but first let me go back to electrodynamics as a warm-up briefly. So let's look at the case without a boundary and with a boundary. So without a boundary, Gauss's law forces you to have zero net charge. If you have a boundary, however, with, say, a Dirichlet condition on the electromagnetic fields, then you can have a net charge quite consistently with the constraints of electrodynamics. And the same thing is true in gravity. So in gravity, if you have a closed space, so if you insist on thinking about global de Sitter, which many of us did for years, then the only sense of energy that you have is that it's constrained to zero. However, the moment you think about a time-like boundary, you have a net stress energy that you can define. And so energy has meaning, and the meaning that it has is very similar to the meaning it has in the famous ADS-CFT correspondence, where also there's a boundary. It's just an extreme example where you take the boundary to infinity in some space-time. So this notion of energy is more specifically given here. Basically what it is say you fix the intrinsic geometry of the boundary, then what you're doing is letting free the extrinsic curvature of the boundary. So if we try to emulate Weinberg and put indices on everything and make it very explicit, take a metric like this, fix the boundary metric, and then the extrinsic geometry is basically the radial or W here derivative of that metric. So that is allowed to fluctuate. The metric itself at the boundary is fixed by a boundary condition. Okay, so there is a notion of energy. So suddenly, if we work even with positive cosmological constant, and we include the generic case of a time-like boundary, we get a notion of energy that makes sense. These things are somewhat subtle, but basically this is the headline. Temperature we can always define via the Unruh effect. And so if we put a boundary somewhere in the space-time, we can measure a temperature associated to that by, say, the Unruh calculation. Theorists like to go to Euclidean and so on, but let's just be physical and do the Unruh detector. And if you put the boundary closer and closer to a black hole horizon or a cosmic horizon, that temperature that you infer from the Unruh calculation gets larger and larger. Okay, so one of the beautiful things that's happened, I should say this thing I'm reporting on is result of the intersection of work by many different groups from many different points of view, and it's been a very interesting time for that reason. So some people in the GR community took a look at this very much for their own reasons and found the following. So let's focus on de Sitter space, but this is a general thing. In de Sitter space, there were those thermodynamic relations I alluded to briefly, but people had been confused. They didn't have a boundary, so this boundary energy, the Brown-York energy, the left-hand side of this equation was just set to 0. And they had a kind of version of the first law where they did try to identify the energy with just the bulk stress energy, which I'm just calling delta E bulk matter. But so they had kind of a first law, but it had the wrong sign. It was confusing, and there's all sorts of literature on how to interpret that. But the moment you consider a boundary, a time-like boundary, and you take into account that the notion of energy there is clear, it's the Brown-York energy, well, then you get the standard sign of the first law of thermodynamics. Okay, so this is as I already said, this is a generalization of the notion of boundary and boundary energy and so on that we have in the ADS-CFT correspondence. In that theory, it is a duality between the wrong sign of the cosmological constant and a conformal quantum field theory. Conformal quantum field theory, any quantum field theory, has an infinite spectrum. And for the purpose of the horizon entropy in de Sitter, that by itself, of course, is inapplicable. And just to anticipate a little bit, our approach will be to, however, deform this system to one with the requisite finite spectrum, deforming it basically by taking the extreme asymptotic boundary of ADS and changing the boundary conditions systematically so that they become those of a finite boundary. And then once we do that, the deformation to de Sitter involves uplifting in the scalar potential in a way that we have a handle on. So I think people are aware of this, but just to put people on the same page, we start from the holographic duality as it works in negative cosmological constant. One thing to know about this, if you don't normally think about it, is that the way the degrees of freedom are arranged is that the boundary of the space-time, which is indicated by this is all in the kind of Penrose diagram sort of picture. The boundary is infinitely far away, and it's where the short scale physics of the conformal field theory lives, and vice versa. Okay, so our approach will be to deform this in a systematic way, making use of some developments in theoretical physics that have been happening in the last 5 or 10 years, in order, as I say, to change the boundary from this very unrealistic one, first of all, to get it to have the needed properties, specifically a finite spectrum. Okay, so how do we change the boundary conditions in ADS-CFT? This is something that we realized kind of belatedly in developing Juan's correspondence, which is that indeed there's some quantum field theory dual to some gravity theory. The quantum field theory is organized in what's called a large N expansion, and there are certain operators you can add, which are called quote-unquote double trace operators, which should be part of the dictionary of the ADS-CFT duality. What was important about it is that these operators by themselves are not associated with individual particles in the bulk, yet they can be added. So with Ofer-Aharoni and others, we noticed that they should play a role in the dictionary, and it was understood best by Berkuz et al. And Witten and so on that the effect they have is to change the boundary conditions. Okay, so we're going to put that together with our desire to make use of the generic topology of time-like boundaries that can be finite. And long story short, we can do that in a known way to render the boundary finite. And in so doing that, we can track the effect on the energy spectrum. So remember, the energy spectrum is now well defined because we have a time-like boundary with a fixed intrinsic geometry. So the energy makes sense. And we can track what it does under a deformation of ADS-CFT to produce first a finite time-like boundary. So once we have the finiteness of the boundary, you might guess, and this is true, whoops, from this picture that if the boundary is finite, then we lose that part of the spacetime that had to do with the super short scale modes of the CFT. So we will obtain in this way a finite spectrum. And this deformation altogether is quite elaborate, as you can see. I mean, it's only 4 parts, so we don't think it's so bad, but it's the case that we have to add these deformation operators in a particular way to controllably obtain, first of all, a finite spectrum that we know, and then to continue to deform in a way that from which the theory produces the de Sitter entropy and energy spectrum that probes the geometry. So to say just a little bit more about that, I said we know what so-called double trace operator to add. For the gravitational sector, it's known as the T-squared operator. And the way you get it is to process the Einstein equations, particularly that radial constraint equation I mentioned, write it in terms of the Brown-York stress energy tensor. Notice that that equation takes the form of trace of the stress tensor equals something. The trace of the stress tensor generates scale transformations, and in a system with one scale, we can trade that for the deformation of the Hamiltonian. Once we have the expression for the deformation of the Hamiltonian, then you might see how we could track the effect on the energy levels. Now, there's a lot more to this. These operators are irrelevant and require some definition. And this proceeds in a way that is inspired by something called the TT bar deformation, where Zamolodchikov and other people showed how you can deform theories in a way where you can track the energy spectrum. What we realized recently is that this very much generalizes to higher dimensions, where we can take the T-squared operator, pull off a piece of it that is of this form, where the stress energy tensor that we plug in to this deformation that we need to do takes this kind of equilibrium form. And then the rest of it, which we'll just call delta T-squared, that part, which is not as simple as this first part that we can, turns out, solve easily, that's the part that requires definition through regularization of the generally irrelevant operator. So the solvable piece of this, the nice thing about it is it captures the most entropic energy levels. So Black holes are the most entropic thing you can do if you assemble a bunch of matter. And similarly for the cosmic horizon, it has the symmetries of this equilibrium form of the stress center that I mentioned. So basically the prescription is to identify the solvable piece which captures the stuff we really need for holography. For this business of trying to understand the microstate count of the horizon, we really care about the most entropic band of energy levels. The kind of fluctuations of bulk gravitons and matter are there. They're interesting, but they're very well calculated instead by the bulk effective field theory and general relativity. So those things are captured by the second piece of the deformation, which we fine-tune to match to those subleading effects of gravity and field theory, while the first piece captures the area term in the entropy. It captures the state count that we need, which again is the thing that we really need holography to get. So here's a formula for the so-called dressed energy that we get from the solvable piece of this operator. And it exhibits the thing that I motivated earlier. It exhibits that we can calculate the dressing of the energy spectrum from this solvable t-squared deformation. And it's a formula for the energies as a function of the energies in the original CFT. And you see if those energies get too large, the square root in this formula can go complex. And so we keep the real spectrum and we get a unitary finite Hamiltonian quantum mechanics theory. That theory, when we include all the things we need to do to deform it to a time-like boundary that's finite and then uplift to de Sitter in ways we know how to do in string theory, gives us the holographic dual for time-like bounded de Sitter. And I don't have time to explain all of it, but just another slide on the second part. So I said there's this double trace operator that we need to add to deform the boundary conditions to get these time-like boundaries. It cuts off the spectrum. And the rest of it, the bulk matter excitations in the system and the rest of the gravity excitations, including the gravitons that we have in 4 dimensions, those we simply and shamelessly tune our quantum systems matrix elements to match to the low energy gravity and effective field theory in the bulk, which only has very crude resolution compared to the resolution available, the capacity available in our finite quantum system. So we easily have the capacity in the system to tune that stuff to match the bulk gravity, the gravitons and bulk matter fields, which are subdominant, very subdominant to the area contribution to the entropy of the cosmic horizon. Okay, so that's the scheme. And the thing that people in the form, okay, there's an uplift of ADS-CFT to de Sitter, where the geometry internally becomes negatively curved. Casimir energy and flux very naturally stabilize it. So we have in mind that as the uplift in a UV complete manner. And in this elaborate deformation, there's a point where we have a boundary that's right outside the horizon. And once you're right outside a horizon, you really can't tell if it's a black hole in ADS or the de Sitter cosmic horizon. And it's at that point that we uplift and continue the deformation in a way that ultimately gives us a finite quantum system with a bunch of states. The top of the finite spectrum, there's a band of energies that reproduces the Gibbons-Hawking entropy as a state count, while the geometry itself is captured explicitly by both the dependence of the boundary energy as a function of the size of the boundary, and also that tuning to bulk gravity that I mentioned. Okay. Okay, so this is, let me just get to the end because I think of this as a generalization of the famous state count in black holes. Let me find it again, where you do a long deformation from some weakly coupled system to a strongly coupled system that corresponds to a black hole. here we're making a deformation from ADS-CFT to time-like bounded de Sitter. Okay, so the formal people might say, what is going on? This is considered to be a horrible problem. So I don't know what old movies Steve liked to watch. Maybe not this one, but you can ask, why is this not too good to be true? And the reason is what I said in words, that there's a piece of this that we can solve and that captures the most important things. The rest of it, we do an enormous amount of fine tuning to match. And we don't mind that in this setting of trying to understand de Sitter quantum gravity, because of the fact that dualities have a weakly coupled side, a strongly coupled side for a given computation. And we don't need holography to calculate graviton scattering. We just don't. We need the experts in the room to do that. What we do need it for is things like the horizon entropy, and the solvable piece of this deformation captures that in an analytic way. So let me stop abusing you with formal physics and just summarize. So the conclusion is this: we should take seriously the generic case of time-like boundaries in cosmology, look for signatures and bound them as much as we can. And I've tried to explain their great utility in understanding quantum gravity and how the ADS-CFT correspondence generalizes to de Sitter spacetime, the positive CC, in a way that makes sense of the various thermodynamic quantities, including the energy and the entropy as a state count. Okay, so let me stop there. Thank you again for this wonderful meeting.
As you know, I'm far from an expert on this kind of stuff, but is it possible that down the road there'll be a numerical prediction for the cosmological constant? I have another one.
I'd love to be able to say yes to that, but I don't see it in this framework. It fits too well with the landscape and with yeah, there's a lot of optionality in these theories. So I mentioned, starting from some CFT and deforming it, and there's an alarming number of ways you could do that consistent with everything we know. So it's again leading us toward what I guess Steve also grappled with, of multiple solutions to that problem.
Okay.
Of course, we could be surprised, so I don't want to say anything.
And my other question was about the observable in the CMB. So then my very first graduate student, Jan 11, worked on circles in the sky, and it's not the same thing, but
right.
it made me remember that work.
Yeah, no, that is a great comment. So there are other things that are sort of vaguely reminiscent of this, like, the way cosmic strings bend light, but that's sort of why I wanted to disambiguate from ordinary sources. It's a different thing, and it's a different thing from the circles you get from, say, thinking about space as a compact hyperbolic space or something where you get circles in the sky. So it's a relative of that, certainly, but in some sense it's just a different ray tracing operation to do this one for this kind of signal. We're not quite there yet. I mean, I tried to get across that there are some interesting theoretical issues with this, which leaves us with different classes of boundary conditions, and getting a handle on exactly which ones we want to focus on. What so we'll try to pick up the pace, because I'm curious to see what happens. Of course, one assumes going in that it'll be a constraint, but there is the logical possibility of some discovery potential, since it hasn't been done. So yeah, I don't know the answer yet. I'm not holding back, but please.
All right. Yes. One last question.
If it's a constraint, what is it a constraint on?
Good. Thank you for that question, Glenna. So it's a constraint on some combination of the size. Let's say we focus on Dirichlet. There's other examples that are interesting too, but it's a constraint on the size, some constraint on the size and density of them. it's not, importantly, it's interesting, it's sort of, to the extent that there's any kind of analogy to lenses, it's like a strong lens because the reflection coefficient is 1. So in that sense, there's not a small number from that. But, so it's not that we're doing one of these things where you have some small amplitude for some process and you dig down to where you can't see it anymore. But the analog of that is the size of the thing. You know, it could be there at some tiny scale and we'd be none the wiser. So
Okay, let's, we have to move on, thank you. But maybe a coffee. Let's thank Ava again.